Welcome back, fellows, to the next jungle expedition into the forest of differentials. This time, we'll not use the physics perspective, FIZZ, but the mathematical one. And in that, we do not really care so much about the difference between differentials and derivatives, because that's just not an important point as long as we don't include differential forms in our theory, which we don't. Instead, we'll focus more on the Jacobian matrix, or total derivative or total differential, and also try to develop an imagination for the whole thing. So I wish you good luck, and let's go. So let's get right into the first point. And let me present to you two newly discovered Picassos, which are, for some reason, exactly about our topic. The first one is about the partial derivative. So the partial derivative, as we know it, is written over here. So in math, we need to take the limits. Same as in physics. And we evaluate the function x plus, let's say, time a little bit in the direction of a standard vector ei minus f of x by t. Let's see what that means. So there's a coordinate system again, x1, x2. There's a point x over here. There's the blue function roof on top of it, because we're talking about scalar fields again. And now we're here. And now we're walking along the direction of E1 in this case, on top of the roof. And in a way, t could be a time where we walk from here to here, walking along with t, always in this direction. And then you can have a derivative, like in the classical 1D case, where this is your axis and this is your graph, and you get the tangent. So that's the partial derivative as we know it. You also know this formula already. Now let's look at the directional derivative. And we'll see it's basically the same. The limit walking with time in the direction, the general direction v in this case. And the rest is the same. So v can just point in any direction, and will again walk on the roof in that direction, parametrize with the parameter t, and we'll find the slope in v direction. We also know this formula already. From a math perspective, this formula is dropping out of the sky right now, but we'll come to that later. So here I will not talk too much about it, but you can see that the directional derivative is actually just a linear combination of the partial derivatives, just as the direction vector v is a linear combination of the ei. And you can stop the video and look at this and see if that makes sense to you. And I will continue, because we do not need that for the next chapter. The next chapter is the total differential, or the Jacobian matrix. So what we want to have from a math perspective is some sort of a derivative, which is not just working on scalar fields or even only one-dimensional functions, but we want to have a derivative from Rn to Rm functions. So really the full set, so to say. And a function like that would look like this over here. So you have component function in each component of big F of x. So big F, capital F, stands for functions which go to Rm. Small f stands for functions going to R. So there's a scalar field in every component of capital F. each takes the variables x1 to xn. And we have m component functions because we want to have vectors in Rn. So what shall this monstrous derivative do if it's based on the concept of the 1D derivative? Well, it shall do the same thing with this linear approximation. Let's see how this could look like. Let's look at the 1D case first. We have a limit. We have seen this formula many times. And it's slightly rearranged so that we have this linear term over here, which makes the whole thing 0. And then really C, this constant, is the slope of the tangent, the best approximation to f in that point, x. So if this expression holds, f is differentiable at the point x, and f prime of x would be c. Now, let's look at the multidimensional case. We have basically the same setup. We have a limit. W is now a vector, as is x, both living in Rn. F taking vectors from Rn. And we subtract f at x, the original point, and we try to come up for this difference with the linear function so that the whole thing gets 0. This linear function is called dfx, and it is applied on W. So what are these double lines over here? This is the norm, and this is basically telling us we are measuring the whole thing with one value, a length. We do not really care about the Rm vectors which come out of these functions, but we want to know, is the difference between all of this in terms of a length, is this going to 0? And then we're content. So this is why we have the norm over here, and we do not really need it over here because we have already scalars. So dfx would be the analogy to f prime of x, but don't write that, but rather see it as a linear function which also takes n vectors and maps it to m vectors and is linear, such as this function is linear. So this would be the setup of this multidimensional derivative. And we'll see that this dfx basically can be represented by the Jacobian matrix. I will just state this here. I will explain it just in 5 minutes, but for the hasty upon you, I want to see the Jacobian matrix, and then maybe you're off to some other business, but take the Jacobian matrix. So dfx, how does it look like? Well, first of all, this whole total differential, as it is called, has the total differentials of the scalar fields in each component. Remember that capital F was consisting of small f's in one column, m of each, m small f's, and now we have like the small Jacobian matrix of these scalar fields in the row. And what we'll find is that each row consists of the gradient of the first scalar field, first component function f1, and transposed so that we can write it in a row. And the same thing for all the other component functions. And then, if you write that out, you'll find the classical Jacobian matrix, which consists of all partial derivatives of all component functions arranged like this. This is the gradient of f1, small f1. Then comes the gradient of the next, and so on until the last one of Fm. So it's a m-row, n-column matrix. And it is called the Jacobian matrix. And I'm sure you've seen that before, but let's look at some small properties of it. For example, take just one row, one gradient of f. So take one row, multiply it with v, some arbitrary direction v, like in the directional derivative. And in fact, it is the directional derivative. As you can see here, this is the scalar product of the gradient of that particular component function, your scalar field, and a direction v. Because let's say this matrix has only one row and you apply it to a column vector v, you will exactly get the scalar product of this row times v. And that was the directional derivative. So each row of the Jacobian is the directional derivative once you multiply it with the direction v. So this Jacobian matrix, all of you have seen. How do we get that actually? Here I want to sneak in a little bit of theory. And before you're all leaving, okay, you probably don't need that for all your calculations and exercises and stuff like that. But if deep inside you are a little curious about how is this famous Jacobian matrix actually created, then don't patronize your curiosity. Give it that couple of minutes. Give it that little try. Just check it out. Maybe it's not that difficult. Probably you won't get it on the first time. That doesn't matter. You will still get a little more comfortable with all the notions and the context. Also, if you still insist on getting it, there's one more chance. But if you're under 18, please leave the room. You cannot hear that. And the others, please close the door. Because what you actually could do, you could open a textbook, chapter Jacobian matrix. But I haven't said that. Also, I don't take responsibility for anything that happens if you do that. So what I'm trying to do now, I'm going to sketch how the Jacobian is developed from this general formula of derivation, which I showed you, just to show you that it comes directly out of this expression. So let's see. First you take this expression, and what do? You take only one component function fi of the big function capital F. Put it in where there was f before. Then you substitute this direction vector w with t times v, where v has just length 1. So that's really the same thing. And t shows you the length. And then, remembering that this linear map dfx is linear, you can get to this expression. And then you have already nearly won the game, because what you find is that over here, you're actually having something which looks like the directional derivative. And it doesn't just look like it, it is x plus tv. And in the next step, instead of putting v, the direction v into it, you take a special direction ej. That is a coordinate direction. And then this whole expression on the left side is actually the partial derivative. And in order to get this whole expression to 0, you can agree that this ominous total differential, the Jacobian matrix, where we do not know yet how it looks like, has to look like the differential, the partial differential for each component function, and depending on which direction vector you put into it. Now you start getting a concrete description what has to be in the Jacobian matrix. And now that's the last step. Remember, this is sort of rushing through it, but you could open the textbook. But the last step is, well, if you put in all directions ej and all component functions fi of your original function capital F, then what you're doing is actually finding the matrix representation for the linear map total differential. Now I'm pausing here because this is something you cannot just swallow like this without having background knowledge about representations. I made a video about that. But in fact, this is a technique, in short, to find each and every single entry of the final matrix. So to not overstay my welcome here, I'm going to go to the next topic, but you can feel free to pause, feel free to look somewhere else. There's lots of different explanations of the same thing, and maybe you'll get some ground there. But the next little more practical thing I want to do is developing an imagination of what is the Jacobian actually doing. And for that, to be able to draw, I pick specific dimensions f of R2 to R2. And so we can put in vectors with x1, x2 components, and we'll get out a vector with the component function f1 and f2, just as we had before. Let's see. I have another Picasso for you. That's the third one already. So let's start over here. We have just, let's say, E1, E2, the basis vectors. And here we have like all the vectors which are in the square. Now we have the big function capital F, which is not linear. And what it does, it maps the square to some sort of banded, curvy patch of something. So all these vectors are now somewhere in here. And now, as we said many times, we are doing linear approximation. And we want to find a map which is linear, mapping the basis vectors, so that I can explain every vector in this white patch by a combination of these two vectors, the red patch. And you see it's not fitting well. But this is only because I draw it so big. If you go to the limits and very local, you'll find a very good approximation. And these vectors are actually the vectors Jacobian matrix times E1 or E2 in the other case. And the Jacobian matrix, as we saw, is defined by the partial differentials of all the component functions. So let's look, for example, at the E2 vector, the image of it. We'll see. So we have change of f2 in x1 direction. So f2 is describing the E2 vector because it's the coordinate in E2 direction. And we see that this coordinate has not just be made longer or shorter, but it has also a change in x1 direction, because E2 went from here to here in x1 direction. So that's the change of E2 in that direction. Also, E2 doesn't have the same coordinate in y direction because, as you see, the red one is slightly above white. So that is df2 by dx2, the change in x2 direction. And the same thing for the e1 vector and f1. It has a change in y or x2 direction and a change in x1 direction. And these are the partial derivatives. And now they are put together in a matrix like this. So for example, these are the coordinates of the first basis vector e1 imaged by the Jacobian. So to explain this red vector over here, the image of e1, you need to take a little bit in e1 direction, that's this guy over here, and a little bit in e2 direction, that's this guy. And this is the way you represent a map with the matrix. So I hope this gives some sort of imagination for the Jacobian. It tells you what would be the best linear way to express your function at a point x locally. And finally, it does something more, because this is a parallelogram, this red square, and we can measure its area by the determinant of these two vectors in columns. So in fact, the determinant of the Jacobian matrix gives us the new area, and compared to the old one, this is the ratio how the area changed by the map in terms of the best linear approximation that is possible. And this is why we'll stumble upon this Jacobian determinant as soon as we start to integrate over different coordinate systems. But that's a story for another day. All right, guys. So let's say you are still a little bit confused about how to imagine the Jacobian matrix. There, I found a nice video, which is only 6 minutes, and the guy explains it very well in terms of animations. And I will give you the link and you can check that out if you think that's necessary. Other than that, I hope you gained some overview over all the mathematical and physical wildlife out there in the jungle of derivation words. And that's all we wanted to achieve in these 2 sessions. So I hope to see you soon, and I would strongly encourage you to resist the temptation to hit anything like or sub there.